Climate change impacts now have become so part of the discussion in the media, in the public, in policy, governance, Paris Agreement, the whole process, that we almost take them for granted. But we also have been looking at various schematics showing climate change impacts on health in the future. But what is involved in projecting climate change impact on health into the future? Is it that straightforward? It turns out that it's not that easy. We got a sense of it when we looked at health vulnerability and how future of health vulnerability under climate change has to be looked at. So a general approach is envisioned like this in this chapter. These are the scenarios used in the assessment number 4, as AR4 it was called, released in 2007. We will see that the current protocol has been changed, but nonetheless the process remains almost identical once the scenarios are determined or agreed upon. So you look at climate change, for the future, you look at population projections, which vary for each scenario, how economic growth will happen based on the choices on energy, science, technology, renewables, etc., etc., climate action, investments, and so on. How the environment will change along the way, how equity, technology, globalization, and other factors will play into the climate projections. But even after we have climate projections, translating that to health impact projections is not that straightforward, because climate models, Earth system models that are used for making climate change projections have uncertainties, as we saw in the temperature projection uncertainty in the last podcast, last chapter, and said this uncertainty is even higher for precipitation projections, for example. Okay. Nonetheless, there are some first principles involved in these, in constructing these models, integrating them forward, and so on. But biology that is involved, for example, vegetation dynamics or human activities like transportation and land use, land cover change, are not purely first principle equations that go into these. So you are mixing pure physics with equations, governing equations, momentum, energy, thermodynamics, mass continuity, and then you're adding chemistry, biology, human activities. So you're creating future projections that are, broadly speaking, in the short term, so in the next decade or two, are related to uncertainties in the models themselves, versus projections to the longer term beyond, let's say, 2050 to 2100, where the scenario uncertainties become bigger part of what is being projected. So these have to be kept in mind when we take the physical climate change projections, chemistry projections, extreme events, sea level rise, and so on, and try to translate them into health impact projections. Very difficult problem, because you are mixing and matching various things. But nonetheless, this is a typical Earth system model that's now used for projections of climate into the future. This particular one is a schematic from GFDL, and you can see how complicated these are. The current set of, or the AR5, which came out in 2014, use what are called representative concentration pathways, as opposed to the 2007 one, which used scenarios which were denoted by these various letters and numbers. So here we went for net CO2 emissions going into the future, leading to the energy imbalance at the top of the atmosphere, as we saw in another chapter before, where representative concentration pathway 2.6 means by the year 2100 you have a net imbalance at the top because of human activities of 2.6 watts per meter squared, and under 4.5 you have 4.5 watts per meter squared imbalance at the top in terms of incoming shortwave energy and outgoing long wave energy, RCP 6 and 8.5. 8.5 is almost the business as usual scenario where you don't have much climate policy, climate action, and so on. And we translate those into the net CO2 emissions, accumulated CO2 emissions, and the resulting temperature, global mean temperature changes ranging from the benign situation where we want to keep it below 2 degrees centigrade, but we will overshoot a little bit, or go all the way to 3.2 to 5.4 degrees C range relative to 1850 to 1900. And the various models used provide a range of warming, some of which are way above this top limit of 5.4 degrees centigrade here. And the resulting atmospheric concentrations end up being various levels, like greater than 1,000 ppm in CO2 equivalent, where again we convert methane, nitrous oxide, HCFCs, and other greenhouse gases into CO2 equivalents using chemistry and global warming potential, right? That we discussed before. So these are the ranges. For RCP 2.6, we would end up with 430 to 480 ppm, but remember, we are already at 420. So essentially, we are already on this business as usual scenario, and we have to soon start drawing down carbon to get back onto these lower targets. Okay, but that's not the whole story. The AR5 also produced something called shared socioeconomic pathways, where the emissions are converted to various sustainability scenarios, governance scenarios, various options chosen by society, global human. So here, representative concentration pathways, which are based on Earth system models, are combined with what are called integrated assessment models, where they worry about mitigation, energy scenarios, economy, agriculture, human activities, bioenergy, and so on and so forth. So Earth system models focus on the physical, climate, biology, chemistry, whereas integrated assessment models take climate as a small module that's providing information and focus on all these socio-economic activities, energy, transportation, land use, mitigation, adaptation, and so on and so forth. So doing this various iterations between them, you end up with reference and mitigation scenarios that include details like food consumption, yield, cropland, and so on, to provide carbon cycle and these carbon emissions and concentrations for the future. Okay, very briefly, if you are a health person, that should suffice. If you are not, you can go back and read more details or listen to my podcasts in the other course. So you end up with these shared socioeconomic pathways, which are in this phase space of looking at degree of global socioeconomic challenges for mitigation going from low to high, and degree of global socioeconomic challenges for adaptation going from low to high. So the middle of the road scenario of shared socioeconomic pathways bring you here. So you have moderate challenges in both mitigation and adaptation. If you want pure sustainable development kind of imposition, then you end up here where adaptation and mitigation challenges are both low. If you are focusing totally on fossil fuel development, where you think you're going to mitigate your way out of climate, then mitigation challenge will be high, but adaptation challenge may be low to medium. And other scenarios like regional rivalries and inequalities and so on end up being either high adaptation or high adaptation and mitigation kind of phase space. Okay. The book also lists, in terms of translating the either climate projections or shared socioeconomic pathways into the health impacts in terms of mathematical models that could be used. Either they are linear, employing linear equations exclusively, or nonlinear, where they have nonlinear equations or the mix of two. So they could be static with no time evolution, or dynamic where time is involved, discrete where objects are treated in a model separately, or continuous where things are evolving continuously in time. They could be deterministic where there is no probabilistic information, so the output depends entirely on prior conditions, the initial conditions or assumptions, and they could be deductive where they are based on some theory and not necessarily governing equations, for example, or they could be inductive and probabilistic where they include randomness using probability distributions. So what if scenarios are made? Inductive models are based on empirical observations, which is very common for health outcomes. We say heat waves produce these kinds of health outcomes, water quality degradation produce these kind of health outcomes, and so on, which are based on past relations. Okay, so let's leave this here and then come back and look at some details on how health impact projections are attempted and what some of the difficulties are. But again, like the vulnerability assessments, these are more about raising all the issues and challenges, and if you want technical details, implementation details, then you'll have to explore the papers. The book chapters provide extensive list of references that are used to make these points, and those papers provide the technical details, which obviously I'm not including in this podcast, where I'm just providing you a primer on all these details that you can then follow up on your own. Okay?